Have you ever thought about what starlight really is? Not the twinkle we see from Earth, but the thing itself, the ancient light that left its source before humans even existed. Every ray that reaches your eyes has traveled across the vacuum for thousands, sometimes millions of years. By the time it arrives, the star that sent it might already be gone. Yet, that light still carries a full report. Temperature, motion, chemistry, distance, an entire biography written in color and wavelength. Tonight, we'll look at how scientists read that message and how a simple beam of light can reveal the structure of the universe. If you enjoy exploring space this way quietly, carefully consider liking or subscribing so others who share that curiosity can join us. Let's begin with the science of starlight. What is starlight? Really? It is something we live with from childhood, so familiar that its true nature can fade into the background. It hangs above bright skylines and over quiet fields, scattered across the dark like small markers in a wide map. People write poems about it. People make wishes on it. Astronomers, though, treat it as a source of data. Behind the calm shine, real physics is at work. Starlight is not magic. It is energy doing what energy does. It is a signal thrown across space. At its core, starlight is electromagnetic radiation. That phrase sounds heavy, but the idea is simple. Electromagnetic is the family name for many kinds of light, from radio waves to gamma rays. The heat you feel from a campfire, the waves inside a microwave oven, the signals that let Wi-Fi move through your home, all belong to this family. Human eyes detect only a small part of it, called visible light. That narrow band is the rainbow we learn in school, and it sits inside a much broader spectrum that stretches to lower energies like radio and infrared, and higher energies like ultraviolet and X-rays. Some parts of the spectrum can burn skin on a summer day. Others warm food. Others bounce off satellites and reach a phone as a video stream. A portion crosses deep space and carries news from distant stars. What we call starlight is mostly visible light, because that is what our eyes evolved to catch and what our sun produces in large amounts. Yet stars are not limited to the visible band. Depending on their mass, age, and surface activity, they also send out infrared light, ultraviolet light, and sometimes X-rays and radio waves. They radiate across the spectrum. We notice the visible part most because our biology is tuned to it, and because Earth's atmosphere lets much of it through to the ground. A star shines because of what happens deep inside it. Its core is under extreme pressure and heat. In that core, hydrogen nuclei, the centers of hydrogen atoms, fuse to form helium. Fusion means joining together. When hydrogen fuses into helium, a tiny amount of mass turns into energy, as described by Einstein's relation E equals mc squared. The released energy moves outward. It is absorbed and re-emitted again and again by the dense gas, stepping slowly toward the surface. When that energy reaches the outer layers, some of it finally escapes to space as light. The light from a star is not one color, but a spread of colors. The full spread is called a spectrum. If you pass starlight through a prism or a grating, you will see a continuous band from red to violet. Physicists compare this to an ideal black body. A black body is a perfect absorber and emitter of radiation. It neither reflects nor favors certain colors. Real stars behave nearly like this ideal. If you plot how bright a star is at each wavelength, you get a smooth curve with a single peak. The position of the peak depends on temperature. Cooler surfaces peak at redder wavelengths. Hotter surfaces peak at bluer wavelengths. Cool and hot in astronomy cover extreme ranges. A relatively cool star, still thousands of degrees at the surface, shines more in red and infrared and looks orange or red to our eyes. These stars tend to be smaller and can live a very long time. Very hot stars shine strongly in blue and ultraviolet. They look blue-white and burn through their fuel faster, with shorter lifetimes. Color is not just appearance, it is a clue. It works like a thermometer at a distance. By measuring the spectrum, or even just the balance between blue and red light, we estimate a star's surface temperature without going near it. Real stars are not perfect blackbodies, so their spectra are not perfectly smooth. There are narrow, dark features, gaps at precise wavelengths called absorption lines. They appear because atoms and ions in the star's outer layers absorb specific colors. Each chemical element has its own pattern of lines, like a signature. Hydrogen shows one set, sodium shows another. Calcium, iron, oxygen, and many more each create their own marks. When we record a star's spectrum and look at the positions of these lines, we learn what elements are present and in what amounts. We also measure how those lines are shifted by motion. If the lines are moved slightly toward the blue, the star is moving toward us. Toward the red, it is moving away. The spectrum becomes a detailed code that carries temperature, composition, and motion all at once. Light also tells us about size and distance. Brightness alone is not enough. A small star nearby can look as bright as a huge star far away. To sort this out, astronomers compare the apparent brightness we observe to the star's luminosity, which is the actual amount of energy it emits each second. Luminosity is a measure of true power, not just how bright something looks from Earth. If we know or can estimate a star's luminosity from its temperature and size, or from its type, then the difference between luminosity and apparent brightness tells us how far it must be. In that way, light becomes a ruler stretched through space. What is striking is how much we learn from light alone. We have never touched a star. We have never flown through a star's surface. Yet we can list temperatures, sizes, surface gravity, chemical mixtures, rotation speeds, ages, and motions. All of this comes from careful study of photons, the units of light. A photon is a tiny packet of electromagnetic energy. It has no mass and no electric charge. In the core of a star, energy is created by fusion and then handed off again and again until it emerges as a stream of photons. A photon's path inside a star is slow and complicated. The gas is so dense that the photon does not move straight outward. It is absorbed and re-emitted many times, like someone trying to cross a crowded room by taking short steps in random directions. This random walk can take tens of thousands or even millions of years from the core to the surface. By the time a photon escapes, many things may have changed far away on any planets that circle the star. Once free of the star, the situation flips. Space is almost empty. A typical cubic meter between stars may hold only a few particles, a lone hydrogen atom, a bit of dust, and nothing else. In that emptiness, a photon finally gets to travel in a straight line. It moves at the speed of light, about 300,000 kilometers per second, roughly 186,000 miles per second. At that speed, a beam of light could circle Earth more than 7 times in 1 second. Over years and centuries, photons cross the gaps between stars. Over millions or billions of years, they cross the spaces between galaxies. Photons do not get tired, and they do not slow down in a vacuum. They just go. Time behaves strangely at that speed, too. From the photon's own point of view, which is a helpful picture rather than a full description, no time passes between emission and detection. For us, the travel time is real. A photon from a star 500 light-years away takes 500 years to arrive. A photon from the Andromeda Galaxy has traveled about 2.5 million years to reach our telescopes. When you look up at night, you are seeing old light. The sky is full of delayed messages. Space is not perfectly clean, though. Dust and gas lie between stars and between galaxies. Dust grains are tiny solids, made mostly of carbon and silicates, sometimes coated with ice. Gas is mostly hydrogen and helium. When starlight meets dust, shorter wavelengths, blue light, scatter more than longer wavelengths, red light. This process is called scattering. It makes some distant objects look redder than they truly are, because the blue part of their light has been redirected away from our line of sight. On Earth, we see a related effect at sunset, when the sun looks red because its light passes through more air and more blue light is scattered away. In space, dust can dim and redden the light from young stars hidden in their birth clouds, and from faraway galaxies whose glow filters through long paths of interstellar matter. Sometimes the photon is not just scattered, it is absorbed. A dust, grain, or a gas molecule takes in the energy. Later, that energy is released again, often at a different wavelength. Thick dust clouds can block visible light almost completely, but infrared light can pass through more easily. That is why infrared telescopes can peer into star-forming regions and see hidden structures that ordinary telescopes cannot. The choice of wavelength matters. Observing across the electromagnetic spectrum is like having different tools in a kit: radio for cold gas, infrared for warm dust, visible for starlight, ultraviolet, and X-rays for hot, active regions near massive stars or compact objects. There is one more influence on a photon's path: gravity. Gravity is not only a pull, it is a shaping of space and time. According to general relativity, mass and energy bend the geometry of space-time. Light follows the geometry. When a photon passes near a massive object, a star, a galaxy, even a cluster of galaxies, its path bends. This effect is called gravitational lensing. It does not mean the photon slows down or feels a tug in the usual sense. It means the straightest possible path through curved space-time is itself curved. Gravitational lensing turns massive objects into natural lenses. If a heavy object lies between us and something even farther away, the nearer mass can focus and distort the background light. Depending on the alignment, the background object may look brighter, stretched into arcs, split into multiple images, or, in a very good alignment, shaped into a ring called an Einstein ring. Astronomers use lensing in two ways: strong lensing, which makes obvious arcs and multiple images, lets us map the mass of the lens, including dark matter we cannot see directly. Weak lensing, a gentler statistical effect, slightly distorts the shapes of many background galaxies and reveals how mass is spread on large scales. Even single stars can act as lenses in a special case called microlensing, briefly brightening a background star when a foreground star passes in front of it. All of this circles back to the main idea. Starlight is information. The spectrum tells temperature and chemistry. The pattern of absorption lines marks elements and motion. The brightness, compared with true luminosity, marks distance. Changes in light over time reveal rotation, spots on the surface, or the presence of orbiting planets tugging gently at the star and making its light wobble. We build instruments to collect more light, split it more finely, and measure it more precisely, because every photon carries a piece of the story. It can feel calm to remember this. Light crosses vast emptiness without a sound. It reaches us without an argument. In a busy world, the night sky offers a steady, quiet record of how things work far away. When your eyes adjust and you look at a star, you receive ancient signals. They come from nuclear fusion in a core, from hot gas at a surface, from space shaped by gravity and thinned by time. The messages arrive as color and line and faint shifts that a sensitive detector can read. Imagine, then, a single photon formed deep in a star. It begins in a crowded, high-pressure place. It moves a tiny step and is absorbed. It is re-emitted and takes another step. This repeats over and over for a very long time. Eventually it climbs into layers where the gas is thinner, and one last emission sends it away from the star. Now it enters the open regions between systems, where the average cubic meter holds almost nothing. It travels straight at light speed, passing clusters of stars, thin clouds of gas, and dust that glows faintly in the infrared. If it avoids dust, grains, and is not absorbed, it keeps going. If gravity from a massive object lies along its path, the photon's route bends smoothly, following the curve of space-time. Step by step, the universe leaves marks on that flight. A cloud may remove a bit of blue light from a whole collection of photons, making a galaxy look redder. A massive cluster may stretch the image of a background galaxy into a thin arc. A compact object may split one source into two. Each effect is not a trick, but a measurement waiting to be made. We build telescopes on mountaintops and in space to collect these signals and turn them into numbers. We compare those numbers with simple models: how a black body radiates, how atoms absorb, how gravity bends paths, and the match tells us that the same laws hold from here to very far away. This is the quiet power of starlight. It is steady enough to measure, rich enough to decode, and honest about distance and time. We cannot hold it in our hands, but we can read it. And when a massive object sits between us and a more distant light source, the bending of that path becomes a lens. It can brighten, distort, or multiply what we see behind it. With good alignment, the background object stretches into a ring. With less perfect alignment, it becomes an arc or a mirrored pair. We have recorded these shapes many times in deep images of the sky. We have seen galaxies appear as rings, arcs, or strange mirrored shapes. All of this happens because gravity bends light. Gravitational lensing is not only striking to look at, it is a practical tool. It lets us study galaxies that would otherwise be too faint or too far to detect. It also lets us map dark matter, the unseen mass that does not glow or absorb. Since we cannot see dark matter directly, we look at how it deflects background light and infer where it sits and how much there is. It is like watching ripples on a pond and working out where an invisible stone must be. Even so, most starlight crosses space without much trouble. Dust and gravity leave marks here and there, but the bulk of the photons travel cleanly. This is where the deeper value begins. As light moves through the universe, it carries history. Photons do not just brighten a scene, they bring information. Every one that reaches an eye or a detector has been in flight for years, centuries, or whole eras. The farther the source, the older the message. A star 1,000 light years away is shown to us as it was 1,000 years ago, when armor clanked in castle courtyards. Inside our galaxy, these delays are measured in decades to millennia. Look beyond the Milky Way, and the clock expands to millions and billions of years. Some of the faintest glows we record set out only a few 100 million years after the universe began. Those photons have crossed most of cosmic time to reach us, carrying news from before the sun formed, before Earth solidified, before any known life. Light does not fade the way sound does in air. A photon does not blur at the edges as it travels. What does change is its wavelength, if space itself stretches while it moves. As the universe expands, it pulls on the light passing through. The wavelengths get longer. Radiation that began as ultraviolet or visible can arrive as infrared, or even as microwaves. The color is shifted not because the photon slows, it always moves at light speed in a vacuum, but because the space between source and observer has grown. This is cosmological redshift. It is one of the key pieces of evidence that the universe is expanding. By measuring how far a spectrum is shifted toward the red, astronomers estimate distance and recession speed. The farther the galaxy, the greater the redshift. It is like the drop in pitch of a siren as it recedes, stretched here across light and deep time. Despite dust, gravity, and expansion, most photons make the trip. They move through the vacuum, nudged only by the mass they pass and the rare cloud of gas or dust. Eventually, a few meet their end in a telescope mirror, a satellite sensor, or the light-sensitive molecules in your eye. The journey stops with a tiny event. One photon kicks an electron in your retina or frees a charge in a CCD pixel. That small interaction becomes a measurement, a point in a graph, a new entry in a catalog, or a quiet moment of understanding. This is not chaos. It is steady motion at the cosmic speed limit, persistent across vast distances. Whether light curves past a galaxy, slips through thin dust, or flies for billions of years alone, it does one job: carry information. In doing so, it becomes our messenger, the link between here and the stars. Long before anyone named photons or understood fusion, there was only light and the urge to explain it. People wondered what light was: substance, wave, particle, or something divine. That question eventually led to one of astronomy's most powerful tools, spectroscopy, the study of how light is spread by wavelength. One path to it began with a prism and Isaac Newton. In the 1,670 seconds, Newton sent a beam of sunlight through a glass prism. Instead of a blur or a faint wash, he saw a clean band of color from red to violet. White light, he realized, is a mixture of many colors. The prism did not stain it. It separated what was already there. He also saw that each color bends by a slightly different amount in glass. That insight turned a trick of light into a foundation for later work. A new question followed. What spectra come from other sources? What does a candle or a hot coal show? What about the sun and the stars? In the early 1800s, Joseph von Fraunhofer, a German optician and master glassmaker, picked up the thread. Using a prism and a telescope, he examined the sun's spectrum with care and saw something unexpected: dark, narrow lines crossing the colors at precise positions. These lines appeared in the same places each time he measured sunlight. When he looked at other light sources, some lines shifted or vanished. Others appeared. Fraunhofer mapped hundreds of lines with striking accuracy. He did not know their cause, but he knew they were real and repeatable. We still call them Fraunhofer lines. The explanation came later, in the mid-19th century, from Gustav Kirchhoff and Robert Bunsen. Heating chemical elements and passing their light through a prism, they found that each element emits bright lines at specific wavelengths. Sodium shows a strong yellow pair. Hydrogen produces a series spread across red, blue-green, blue-violet, and violet. Every element has its own pattern, like a barcode. Kirchhoff noticed that the dark lines in the sun's spectrum match bright lines from glowing elements. The conclusion was bold and simple. The sun, and by extension, the stars contain the same elements found on Earth. The same physics applies in both places. This was a turning point. Light was not only illumination, it was data. Spectroscopy became a tool to read temperature, composition, and motion. With this tool, astronomy changed. By splitting a star's light and measuring the positions and strengths of its lines, we learned that stars are mostly hydrogen and helium. We saw which stars move toward us and which move away, using slight shifts in their lines due to the Doppler effect. We found gas clouds between us and distant galaxies because they imprint their own lines on background light. We organize stars by their spectra and temperatures into the O-bar FGKM sequence, from the hottest blue-white stars to the coolest red ones. We recognized quasars, extremely energetic, distant sources, by their broad, highly redshifted lines. We detected planets around other stars by tracking minute, regular shifts in stellar lines as planets pull their hosts back and forth. It is worth pausing on how direct this is. With a prism or a diffraction grating, we can analyze a faint beam from millions of light years away and list the elements present. No need to visit. The spectrum is the sample. The precision of this method rests on the structure of atoms. An atom has a small nucleus of protons and neutrons surrounded by electrons. Electrons occupy allowed energy levels. These levels are not little planetary orbits but stable patterns, like standing waves. An electron can move to a higher or lower level only by absorbing or emitting a photon, whose energy exactly matches the difference between the two levels. That rule explains lines in spectra. When starlight passes through a cooler gas like the outer layers of a star or an interstellar cloud, electrons in the gas absorb photons of very specific energies and jump upward. Those exact wavelengths are missing when the light reaches us, so they appear as dark gaps, absorption lines. Each element has its own set of allowed jumps, so each makes a unique pattern. A spectrograph reads that pattern and identifies the elements along the line of sight. The mirror image of absorption is emission. If a gas is heated or excited by radiation, its electrons jump up and then fall back down, releasing photons with precise energies. Viewed directly, that glowing gas shows bright, thin lines at those wavelengths, emission lines. Hydrogen provides a clear example. In visible light, its most famous set of transitions is called the Balmer series. One line, H-alpha, sits at about 656 nanometers in deep red. It lights up star-forming regions where hydrogen is excited by young, hot stars. When we image nebulae through a filter that passes only H-alpha, filaments and arcs of ionized gas stand out with clean contrast. The choice between absorption and emission depends on the geometry and the temperatures involved. If a continuous spectrum from a hot, dense source passes through a cooler gas, we see absorption lines cut across the rainbow. If we look at the hot, thin gas itself and it is excited, we see bright emission lines against a darker background. Under some conditions, we even see both, or complex blends, as in the layered atmospheres of stars and the mixed environments around young clusters. These patterns are reliable because the energy levels of electrons are fixed by quantum rules. That gives us a stable code to read. Once we measure the positions of lines, we can also measure their shifts. A small move toward shorter wavelengths means the source or the absorbing gas is moving toward us. A move toward longer wavelengths means it is moving away. The size of the shift tells us the speed along our line of sight. Repeated measurements over time reveal changes in speed, which can indicate a star's rotation, surface activity, or the pull of orbiting planets. Line widths carry other clues. Thermal motion, pressure, and turbulence can broaden lines in predictable ways. Spectroscopy reaches beyond stars. In galaxies, it separates light from young, hot stars, strong blue continuum, certain emission lines, and old, cooler populations, redder continuum, different line strengths. In the interstellar medium, it traces cold hydrogen by its 21-centimeter radio line and molecules by their rotation and vibration lines in the radio and infrared. Around black holes, it shows very high energies and fast motions. Across cosmology, it measures redshift and builds the map of large-scale structure. All of this depends on how light and matter trade energy in clean steps. Zoom in on a beam of starlight and you would not find a smooth smear. You would see an organized pattern of thin features, some dark, some bright, laid across the colors. The positions and depths of those features form the signature of the elements in the source and along the path. They do not depend on taste or style. They are set by physics and repeat wherever the same conditions exist. Atoms are small, but their rules scale up to stars and galaxies. Picture the atom again, a tiny nucleus, electrons in allowed states, and transitions that absorb or emit at exact energies. A photon with too little energy does nothing. With too much, it also misses the mark. Only the right amount triggers a jump. That selectiveness is why spectral lines are thin and precise. It is also why we can trust them across long distances and long times. Hydrogen, being the most common element, anchors much of this work. Its Balmer lines mark temperatures in stellar photospheres and glow in emission in H2 regions where gas is ionized by young stars. H-alpha at 656.28 nanometers is especially useful. It traces shock fronts, expanding shells, and filaments in nebulae. It helps measure the motions of gas in galaxies. It links what we see in images to the underlying processes of heating, cooling, and star formation. When electrons drop from higher levels to lower ones, they return energy to the light field as photons with very specific colors. An ensemble of excited atoms does this together, creating a set of bright marks across the spectrum. Watch a lamp filled with sodium vapor and you see its yellow line. Look at a neon sign and you see its complex red-orange glow made of many emission lines. In space, the same physics applies in thin gases lit by nearby stars, shocks, or radiation from hot objects. Under those conditions, if you observe the glowing gas itself, such as the gas in a nebula or in a flame, you will mostly see emission lines. If you look at a continuous light source that shines through a cooler gas, like a star's hot interior shining through its cooler outer layers, you will mostly see absorption lines. Those lines are not decoration. They are tools. By matching their positions to known laboratory patterns, we identify elements in places we will never visit. Hydrogen, helium, calcium, iron, sodium. Each leaves a set of narrow gaps at exact wavelengths. No sample jars, no probes into a supernova. The light carries the evidence. A prism is enough in principle. Modern spectrographs do the job with far more precision. The lines do more than name the elements. Their depth and shape also track how much of each element is present. Deeper lines usually mean more atoms are absorbing at that wavelength. Temperature matters too, because it sets how atoms are ionized and how electrons are distributed among energy levels. That changes which lines are strong. As an example, hydrogen's visible absorption lines are strongest in stars around 10,000 kelvins, where hydrogen atoms are in the right state to absorb efficiently. Motion leaves its mark as well. When a source moves toward us, all its lines shift slightly to shorter wavelengths, a blue shift. When it moves away, they shift to longer wavelengths, a red shift. This is the Doppler effect, applied to light. With careful measurements, astronomers can determine speeds of a few meters per second in nearby stars and many thousands of kilometers per second in distant galaxies. The result is a clean bridge from atomic physics to large-scale motion. The same logic applies beyond stars. Any object that emits or absorbs light can be studied this way. Gas clouds in the Milky Way, comets shedding vapor, thin planetary atmospheres, even the faint glow of exoplanet air seen during a transit, all reveal themselves through spectral features. A shallow dip from water vapor or methane in a distant planet's spectrum is interpreted with the same rules first tested in 19th century flames. One method, many targets. What makes these lines so dependable is their origin in fixed atomic energy levels. Hydrogen's Balmer series always falls at the same set of wavelengths. Sodium's well-known yellow doublet remains sharp and repeatable. Helium's lines sit in their precise places in the violet and yellow. These patterns are not fashion, they are consequences of quantum rules. Because the rules are the same everywhere, we can trust a line seen in a faint smear of light from a faraway galaxy to mean the same thing it does in a laboratory tube. From these simple marks, we build histories. A line from hydrogen, a pair from oxygen, a trace from nitrogen. Together they point to star formation and the recycling of elements. We learn where gas is heated, where it cools, and how elements forged in old stars seed the next generation. Light becomes a record keeper. A star can seem unknowable at first glance, a bright, unreachable sphere of hot gas. Yet we know a great deal about stellar makeup. We know that hydrogen and helium dominate, and that heavier elements such as oxygen, carbon, nitrogen, magnesium, silicon, and iron appear in smaller amounts. We know how those mixes vary from star to star and change over time. We learn this not by touching a star, but by reading its light. A spectroscope shows a star as more than a blur. The cooler outer layers imprint patterns onto the light, produce deeper within. Spread the light into a spectrum, and you see many narrow dark features. Each feature is an element speaking at its assigned wavelength. Hydrogen, helium, iron, calcium, sodium, each taps a specific set of notes. The positions are fixed by physics. Only motion can slide the whole pattern left or right. and then by the same amount for all lines. This is spectral analysis. Compare the stellar pattern to laboratory standards and list the elements. The sun's spectrum, for example, reveals a composition dominated by hydrogen and helium, with traces of heavier elements. Calcium leaves some of the most prominent lines in the violet part of the sun's spectrum, the Ca2, H and K lines. They are strong enough to be seen with modest instruments and are widely used to track magnetic activity in stellar atmospheres. History adds a telling example. In 1868, during a solar eclipse, the French astronomer Jules Janssen observed a bright yellow line in the chromosphere that did not match any known element. Soon after, the British astronomer Norman Lockyer saw the same line and proposed a new element, helium, named for Helios. The Sunday, only decades later, was helium found on Earth, trapped in certain minerals. For a time, it was known in spectra before it was known in the lab. That discovery showed how far light alone could take us. Counting lines and measuring their depths is not the whole story. Temperature, pressure, and magnetic fields reshape line strengths and widths. Pressure can broaden lines through frequent collisions. Thermal motion broadens them too, with hotter gases showing wider features. Magnetic fields split lines into nearby components, a pattern called the Zeeman effect. With models that include these influences, astronomers recover element abundances, temperatures, pressures, and field strengths. Repeated observations show how these properties change over time. Surveys of many stars reveal patterns in chemistry across the galaxy. Some stars are metal-rich. In astronomy, metals means all elements heavier than helium. Others are metal-poor, especially ancient stars formed when the universe held few heavy elements. Their spectra show very little iron or silicon, supporting the idea that the first generations of stars forged the heavier elements and then spread them through supernovae. We even find stars with unusual element ratios that hint at past exchanges with companions or birth in now dissolved dwarf galaxies. The same tools reach other galaxies. Though their light is faint, their spectra still list ingredients. We measure the gas around their stars, the rates at which new stars are forming, and the presence of active nuclei. We detect the intergalactic medium because it imprints thin absorption features onto the light from bright background sources. A single spectrum taken through a telescope can cross millions of light years and still deliver identifiable lines. Hydrogen, the universe's most common element, sits at the center of much of this work. Its Balmer lines, in visible light, follow a simple mathematical pattern. The deep red H-alpha line, at about 656.28 nanometers, traces ionized gas in star-forming regions and in the arms of galaxies. In very hot stars, hydrogen can be so ionized that Balmer absorption weakens. In cooler stars, the lines can be stronger. In dense environments, collisions smear the lines wider. Each change encodes conditions at the source. These are practical tools, not just curiosities. With spectra, we extract stellar temperatures and surface gravities. We measure chemical abundances element by element. We track rotation because spinning spreads line wavelengths by the Doppler effect across the star's disk. We map magnetic activity through line splitting and broadening. We detect orbiting planets when their tiny tugs make a star's lines slide back and forth on a regular schedule. We even probe planetary atmospheres during transits by comparing a star's spectrum with and without the planet in front, looking for the planet's thin, additional absorption. Light alone lets us do all of this. No landers, No samples, just careful measurements of photons. The shift of a line indicates motion. Its depth tracks abundance. Its width and shape speak to temperature, pressure, and fields. A star's age and history come into view through these combined readings. What began as a rainbow becomes a set of numbers, and those numbers become a physical picture. You can test the idea with a simple analogy. Stand on a quiet street and listen to a fire truck approach. The siren sounds high-pitched as it comes toward you. As it passes and moves away, the pitch drops and fades. That is the Doppler effect with sound. The motion of the source squeezes or stretches the sound waves, changing their frequency. The same principle applies to any type of wave. At its core, the Doppler effect is about relative motion. When a source moves toward you, the waves in front are compressed into shorter wavelengths and higher frequencies. When it moves away, the waves are stretched into longer wavelengths and lower frequencies. With sound, your ears register this change as a rise or fall in pitch. With light, your detector registers it as a shift in color. Light also travels as waves, even if we rarely think of it that way. Electromagnetic waves have a frequency, how often a crest passes each second, and a wavelength, the distance between crests. When the source of light moves, those waves shift. If the source moves toward us, the crests bunch up and the wavelengths shorten. The spectrum slides slightly toward blue. We call that a blue shift. If the source moves away, the crests spread out, the wavelengths lengthen, and the spectrum slides toward red. That is a redshift. For everyday objects, the effect is too small to notice because light moves so fast, about 300,000 kilometers per second. A car's headlights do not turn reddish as it drives away from a garage. In space, where objects travel thousands of kilometers per second and distances are vast, the effect becomes measurable and useful. Astronomers read this shift by examining spectral lines, the same element, fingerprints, left by hydrogen, calcium, sodium, iron, and others. If the lines appear where laboratory standards say they should, the star's motion along our line of sight is small. If the lines are displaced toward the red or blue, the star is receding or approaching. The amount of shift gives the speed. This turns color changes into a speedometer that works even when a star's position hardly changes on the sky. The method scales well. In binary star systems, two stars orbit a common center. As one moves toward us and the other moves away, their lines shift back and forth in a timed pattern. From that pattern, we can derive their speeds, estimate their masses, and map the shape of their orbits. The same idea extends to planets. A planet's gravity makes its star wobble slightly. That wobble slides the star's spectral lines by tiny amounts in a repeating cycle. Sensitive spectrographs can detect these shifts and reveal the presence of an exoplanet even if the planet itself is too faint to see directly. The signal is small, but with stable instruments and careful calibration, the pattern stands out. Redshift is even more revealing on the largest scales. In the early 20th century, measurements of distant galaxies showed that their spectral lines were shifted toward the red, and the shift grew with distance. Edwin Hubble and others assembled the data and recognized the pattern. The simplest interpretation is that the universe is expanding. Galaxies are not flying through a fixed space away from us. Rather, space itself is stretching, carrying galaxies with it. As space expands, light traveling through it is stretched as well, shifting to longer wavelengths. This is cosmological redshift. It looks like a Doppler shift, but its cause is the expansion of space rather than motion through space. Cosmological redshift underpins modern cosmology. It supports the idea that the universe had a hot, dense beginning and has been evolving ever since. The more distant a galaxy, the longer its light has traveled and the more it has been stretched. Some of the earliest galaxies are now detectable only in the infrared or even longer wavelengths. Observatories designed for infrared work, such as space telescopes with very cold optics, are built to capture these stretched signals from the young universe. Redshift also lets us estimate how fast the universe is expanding. The proportionality between distance and recession speed is called the Hubble constant. Measuring it precisely has become a central goal. Independent techniques using nearby standard candles and the cosmic microwave background present values that differ slightly. A disagreement called the Hubble tension. The difference may come from unknown systematics or from physics we do not yet include. Either way, the redshift distance link remains a key ruler for the cosmos. Not every galaxy shows a redshift. The Andromeda galaxy, our large neighbor, shows a blue shift because it is moving toward the Milky Way. The two will likely merge in about 4 billion years. Stars are so far apart that most will miss each other, but the overall structures will combine. We know this motion from the pattern of Andromeda's spectral lines and from precise measurements of its movement across the sky. Our own motion matters too. The Sun and its planets orbit the Milky Way's center at roughly 220 kilometers per second. Earth orbits the Sun, and Earth rotates daily. These motions produce small, predictable Doppler shifts. Astronomers correct for them to isolate the motion of the objects being studied. It is like measuring a distant ship's speed from a moving boat. You must subtract your own motion to get the ship's true velocity. Once you see how motion and wavelength connect, color stops being only appearance. It becomes a carrier of information. The spectrum records not just what something is made of, but where it is headed and how fast. Combined with brightness and position, it gives a fuller map of how the universe changes with time. Color also reflects temperature. Stars are not perfect white points. They are close to blackbodies objects that emit a continuous spectrum shaped mainly by temperature. The hotter the surface, the shorter the wavelength at which the emission peaks. The cooler the surface, the longer the peak wavelength. This is Wien's law. Very hot stars look blue-white because their peak lies in the blue or ultraviolet. Cool stars look orange or red because their peak lies in the red or infrared. The human eye can pick up some of these differences, even at night. In Orion, Betelgeuse in the shoulder appears reddish because it is cooler. Rigel in the foot appears bluish-white because it is much hotter. Approximate numbers make this clear. A cool red star might have a surface temperature near 3,000 degrees Celsius. A hot blue star can exceed 30,000 degrees. Our Sun, often drawn as yellow, actually emits most strongly in the green part of the visible spectrum, but because it radiates across the whole visible band fairly evenly, and because Earth's atmosphere affects the color we perceive, we usually see it as white with a warm tint. These differences are more than cosmetic. They signal how energy flows from a star's surface and how rapidly that star uses its fuel. Astronomers have organized these behaviors into a practical sequence based on spectra and temperature. O, B, A, F, G, K, M. The order looks odd because it grew from earlier systems that ranked stars by hydrogen line strength before the physics was fully understood. Rearranged by temperature, it now runs from the hottest O-type stars to the coolest M-type stars. Students keep the order in mind with simple memory aids. The exact phrasing matters less than the idea that the sequence traces a smooth change in temperature and spectral features. O-type stars sit at the top. They are very hot, above about 30,000 degrees Celsius, massive, and bright. They pour out ultraviolet radiation and live only a few million years before ending in powerful events. B-type stars are still hot, between roughly 10,000 and 30,000 degrees, blue-white, and less common than cooler stars. Their spectra show strong helium lines and relatively weaker hydrogen lines compared with types below them. A-type stars are cooler still, about 7,000 to 10,000 degrees. They often stand out in the night sky and show very strong hydrogen absorption. Sirius is an A-type star and appears bright white to the eye. F-type stars, around 6,000 to 7,500 degrees, look white with a faint yellow cast. Their spectra show hydrogen lines, along with many lines from heavier elements, metals in astrophysical language. Chemistry in their atmospheres becomes richer as temperature falls. G-type stars follow. The Sun is a G-type star near 5,500 degrees at the surface. G-stars are common and stable, with lifetimes measured in billions of years. Their spectra include hydrogen lines and many metal lines such as iron, calcium, and magnesium. K-type stars are cooler, between about 3,500 and 5,000 degrees. They emit orange light, remain bright, and often host planetary systems. They burn hydrogen more slowly than the Sun and can live longer. Many are older than the Sun and show quiet, steady output. M-type stars, red dwarfs, are the coolest common main sequence stars, with surface temperatures near 3,000 degrees or lower. They are small and faint but extremely numerous, likely making up the majority of stars in the Milky Way. Because they burn fuel so slowly and are low in mass, they can shine for trillions of years, far longer than the current age of the universe. None has had time to reach the end of its life yet. The extremes highlight the differences. Red dwarfs are modest in brightness, patient in evolution, and stable for long stretches. At the opposite end, hot blue giants and O-type stars radiate enormous power, live quickly, and often end as supernovae, neutron stars, or black holes. The two groups share the same physics but follow different life stories because mass and temperature set the pace. Color and temperature tie into other key properties. In general, hotter stars are more massive and far more luminous. Cooler stars are less massive and dimmer. A single blue star can outshine the Sun by factors of tens of thousands, while a red dwarf may emit only a tiny fraction of the Sun's light. A blue star can outshine the Sun by a factor of 100,000, while a red dwarf may emit only a fraction of the Sun's light. Their long, steady lives make them strong candidates for hosting life if their flares are not too harsh. Spectral classification, though, is about more than surface temperature. It relies on the detailed pattern of absorption lines, which carry information about a star's atmosphere, surface gravity, and chemical makeup. The main sequence letters O through M are refined with numbers from 0 to 9. A G2 star, like the Sun, is a little hotter than a G5 star, but cooler than a G0. This added step helps place a star more precisely along the temperature curve. Astronomers also add luminosity classes to show size and surface gravity. Class I for supergiants, II for giants, and V for main sequence, dwarf stars like the Sunday. Put the spectral type and the luminosity class together, such as G2V or M23, and you get a compact summary of temperature, radius, and general stage of life. Beyond the main sequence, the variety grows. Red supergiants, such as Betelgeuse, are cooler than the Sun at the surface, but so large that they outshine hundreds of thousands of smaller stars. White dwarfs, in contrast, are tiny stellar remnants. Many are hotter than typical main sequence stars, yet their small size makes them faint, so they require a telescope to see. Color is not decoration. It is physics made visible. It points to the heat flowing out of the surface, to the reactions in the core, and to where the star sits in its life cycle. With nothing more than the spectrum behind that color, we can read a star's temperature, gravity, composition, and motion. The glow becomes a data stream, not just a sight to admire. Among the many elements that write into starlight, two dominate: hydrogen and helium. They are the simplest atoms and the most abundant. Hydrogen sits first on the periodic table with 1 proton and 1 electron. It accounts for roughly 3/4 of normal matter. It lives in stars, in cool interstellar clouds, in the gas giants, and in water and organic molecules. Helium, with 2 protons and, usually, 2 neutrons in the nucleus and 2 electrons, is the runner-up at roughly 1/4 of normal matter. Both formed in the first minutes after the Big Bang, when the universe was hot and dense. As it cooled, protons and neutrons joined into light nuclei. Hydrogen emerged mostly as single protons that later captured electrons. A significant fraction of helium formed as well. Heavier elements needed the later furnaces inside stars. Hydrogen's simple structure leads to a central role in how stars shine. When enough gas gathers, gravity compresses it. Pressure and temperature rise in the core. Around 10 million degrees Celsius, hydrogen nuclei begin to fuse into helium. In the Sun, the main chain starts with 2 protons occasionally colliding, closely enough that one turns into a neutron, creating deuterium, 1 proton plus 1 neutron, while releasing a positron and a neutrino. The deuterium quickly combines with another proton to make helium-3. 2 helium, 3 nuclei, then merge to make helium-4 and return 2 protons to the pool. Each step releases energy. That energy moves outward and, after many interactions, escapes as light. The numbers are large but steady. Every second, the Sun fuses roughly 600 million tons of hydrogen into helium and loses about 4 million tons of mass, converted into energy by E equals mc squared. This has gone on for more than 4 billion years and should continue for about 5 billion more. Hydrogen is also a clear messenger in spectra. Its Balmer series invisible light includes thin, well-placed lines, especially H-alpha near 656.3 nanometers. H-alpha highlights star-forming regions where hot, young stars energize surrounding gas. It traces solar activity in the Sun's chromosphere. It marks expanding shells and filaments in nebulae. In very distant objects, the ultraviolet Lyman series becomes essential. Although Earth's atmosphere blocks most ultraviolet, space telescopes can measure it, and the Lyman alpha line at about 121.6 nanometers is a key tracer of hydrogen gas across cosmic distances. Light from faraway quasars carries dozens to hundreds of small Lyman alpha absorption features from intervening clouds, a pattern known as the Lyman alpha forest. It maps the web of gas between galaxies. Helium's story complements hydrogen's. It was also forged in the early universe, It was first identified in the sun's spectrum in 1868, when astronomers recorded a yellow line that did not match any known element then on Earth. Only later was helium found in terrestrial minerals and gases. In hot O and B-type stars, helium absorption lines are strong. In cooler stars, they weaken because helium atoms are harder to excite at low temperatures. As stars age and run low on hydrogen, their cores contract and heat further. Near 100 million degrees, helium can fuse through the triple alpha process to make carbon and then oxygen. This stage is shorter than hydrogen burning but crucial for building the heavier elements that later enrich space. Hydrogen and helium give clean, dependable marks. Heavier elements often produce crowded forests of lines. By contrast, hydrogen's and helium's patterns are simpler, which helps when we need firm anchors for measuring motion and temperature. We see them in planetary nebulae, the thin shells of gas ejected by dying sun-like stars where hydrogen and helium emission lines stand out. We see them in supernova remnants, where line strengths and shapes help reveal the past makeup of the exploded star. Even in extreme objects like white dwarfs and neutron stars, thin layers of hydrogen or helium can leave recognizable features that hint at their histories. On the largest scales, the relative amounts of hydrogen and helium give a powerful test for cosmology. Observations of ancient gas clouds and the cosmic microwave background agree with the prediction that the early universe would produce about 75% hydrogen and about 25% helium by mass, with trace amounts of deuterium and lithium. This match between theory and measurement is one of the pillars of the Big Bang model. To see why these elements make such precise lines, we return to atoms and their energy levels. Electrons are not free to take any energy they like. They occupy allowed levels set by quantum rules. When an electron jumps from one level to another, it absorbs or emits a photon whose energy equals the difference between those levels. Because the differences are fixed, the wavelengths are fixed. This creates thin spectral lines at exact positions. One especially useful set for hydrogen is the Balmer series. These lines appear when electrons fall to the second energy level, n equals 2. From higher levels, n equals 3, 4, 5. Each drop produces a photon with a specific wavelength. In visible light, the strongest is H-alpha at about 656 nanometers in deep red. Next is H-beta near 486 nanometers in blue-green, then H-gamma near 434 nanometers, and H-delta near 410 nanometers. As the starting level increases, the lines shift toward shorter wavelengths and get closer together. They crowd toward a limit near 364.6 nanometers, called the Balmer limit, beyond which the pattern blends into a continuum. Hydrogen also sings in other bands. In the ultraviolet, the Lyman series appears when electrons fall into the ground state, n equals 1. These jumps cover larger energy differences, so the photons have higher energies and shorter wavelengths. Lyman alpha, at about 121.6 nanometers, is central to studies of young galaxies and the intergalactic medium. Because Earth's air blocks far ultraviolet light, we observe Lyman lines from space or by catching red-shifted ultraviolet that has slid into visible or infrared wavelengths. In the infrared, the Paschen series shows up when electrons fall into the n equals 3 level. These lines are valuable for looking through dust because infrared light passes more easily through dusty regions that block visible light. Deeper in the infrared, the Brackett, Fund, and Humphreys series involve falls to n equals 4, 5, and 6. Each family follows the same rule. Electrons land on a fixed base level. The starting level sets the exact wavelength. The sequence of lines marches toward a limit as the starting level rises. It is striking that all of this structure comes from hydrogen, the simplest atom, a single proton, and a single electron. Its simplicity is exactly why the pattern is so clean. Electrons are selective. They do not accept any random energy. They require a match. That selectiveness fixes the wavelengths and lets astronomers build precise tools. This regularity helped shape early atomic theory. In the late 19th century, Johann Balmer noticed a simple formula that reproduced the visible hydrogen lines. Later, physicists generalized it into the Rydberg formula that predicts wavelengths across the different hydrogen series. Niels Bohr then proposed a model in which the electron moves in quantized orbits around the nucleus and emits or absorbs light only when it jumps between them. The Bohr model does not capture every detail of real atoms, but it explains the Balmer pattern and points to a deeper framework. Modern quantum mechanics replaces orbits with wave functions and explains energy levels through the solutions to the Schrödinger equation and, for high precision, relativistic corrections. It adds the ideas of angular momentum, quantization, selection rules that decide which transitions are allowed, and small shifts and splittings caused by fields and interactions. These refinements explain line widths, shapes, and fine structure, and they match what we measure in laboratory lamps and in starlight. In practice, astronomers use this well-tested physics to turn spectra into temperatures, densities, motions, and chemical lists. So the next time a spectrum is spread across a screen, those thin lines are not decoration. They are the result of electrons changing states in exact steps. Hydrogen and helium supply many of the clearest marks. Heavier elements add their own patterns. Together they write the physical conditions into the light we receive. The ideas began with prisms and careful sketches. They now live in precise instruments and detailed models. Yet the core picture remains simple. Electrons jump between allowed levels, and the jumps leave signatures governed by the elegant but slightly mysterious rules of quantum mechanics. At the simplest level, a spectrum is a map of how electrons move inside atoms. Each atom has its own allowed energy levels, and when electrons jump between them, they leave marks at exact wavelengths. Those marks are spectral lines. They act like fingerprints, but a musical analogy also fits. Each element plays a set of notes in light. Hydrogen's notes are clean and strong, easy to pick out in a noisy scene. Heavier atoms add chords and harmonics, enriching the pattern, but also making it busier. In crowded places, the core of a galaxy, the edge of a supernova remnant, hydrogen's pattern still stands out. Its lines remain steady guides to temperature, motion, density, and composition. We see them in emission and absorption, in stars and nebulae, in nearby galaxies and the distant universe. Hydrogen's Lyman alpha line is especially important for the early universe. By the time this ultraviolet line reaches us from very distant galaxies, expansion has stretched it into the infrared. Infrared telescopes can catch it and use its shift to clock how far back in time we are looking. In that way, each series, Balmer in visible light, Lyman in ultraviolet, Paschen and Brackett in infrared, becomes a different voice of the same atom. All are made by electrons changing levels. None are random. Quantum rules set which jumps can happen and what wavelengths they produce. Simple rules, big consequences. The order we see in hydrogen's spectrum reminds us that, beneath the variety of the sky, there is structure we can trust. To turn that trust into measurements, we need tools that translate starlight into data. A telescope is the first step. Its mirror or lens gathers photons and directs them to an instrument that can spread the light into a spectrum. Bigger telescopes collect more light, which means fainter targets and finer details. That matters for spectroscopy, where we want enough photons at each wavelength to draw sharp, reliable lines. Many observatories sit on dry, high mountains to cut down on blurring and absorption by air. Others work above the atmosphere, where ultraviolet and much of the infrared can be captured without loss. Space telescopes remove air's distortions completely and keep steady focus for long exposures. The device that separates light is the spectrometer. Most modern spectrometers use a diffraction grating, a surface with many fine grooves that send different wavelengths off at slightly different angles. The result is a fan of colors arrayed across a detector. A prism can do this too, but gratings are more precise and easier to tune. The detector is usually a charge-coupled device, CCD, or a related sensor that records how much light arrives at each pixel. Line by line, wavelength by wavelength, the instrument builds a spectrum. Resolution is a key idea. Spectral resolution tells how well the instrument can separate nearby wavelengths. High resolution reveals subtle splits and blends, small shifts from motion, and delicate structure in the lines. Low resolution is better for very faint objects and for quick surveys. Both have a place. A high-resolution view is like standing close to a painting and tracing brush strokes. A low-resolution view is like stepping back to see the full scene. None of this works without calibration. Instruments drift, temperatures change, optics flex. To keep measurements true, astronomers observe lamps filled with known gases that produce well-measured lines. They also note the instrument's response across wavelengths and subtract background light. Because Earth spins and orbits, and because observatories move with Earth's surface, the wavelengths we record are shifted by our own motion. Software corrects for these effects, so the final spectrum reflects the source rather than us. Some spectrometers use cross-dispersion, which spreads light in two directions so that multiple spectral orders can be recorded at once. That increases the wavelength coverage without sacrificing resolution. Others are built to work at specific bands: ultraviolet for hot, high-energy processes, infrared for cool dust and molecules, X-ray for extreme environments around neutron stars and black holes. The same physics applies across the bands. Only the instruments change. The data volume is large. Software measures line positions, depths, and widths, fits profiles, estimates, temperatures and chemical abundances, and extracts velocities from tiny shifts. It is forensic work at cosmic distance. The same optical rules that explain a soap bubble's colors and a neon sign's glow explain the spectra of supernovae and quasars. One language light connects the small to the large. Stars look still to the eye, but they move in many ways. They orbit the galaxy, drift relative to neighbors, and often circle companions. Spectroscopy is one of our best motion detectors because motion changes wavelength. Radial velocity, the speed along our line of sight, shifts every spectral line. A blue shift means motion toward us. A red shift means motion away. The amount of shift tells the speed. High-stability spectrographs can detect changes of just a few meters per second in nearby stars. That precision reveals planets. A star with a planet does not sit perfectly still. It moves in a small orbit, and its spectral lines slide back and forth on a regular schedule. The same method maps binary stars. As the pair orbits, one star's lines shift blue, while the others shift red. Then they trade places. From timing and amplitude, we can estimate masses and the shape of the orbit. On the largest scales, redshift maps expansion. Distant galaxies show lines shifted to longer wavelengths, and the shift grows with distance. That pattern supports the picture of a universe in which space itself is stretching. The shift is not just from motion through space, it comes from the growth of space between us and the source. Infrared observatories catch these stretched signals from early times when the first galaxies were forming. The relation between redshift and distance also gives the expansion rate, called the Hubble constant. Different methods currently give slightly different values, a tension that may point to new physics or to small biases in our measurements. Either way, the link between shift and distance remains a central tool. Not all motion is along the line of sight. Proper motion tracks how a star slides across the sky over years. It is tiny in angle, but adds up with time. Photographs spaced decades apart show nearby stars creeping against the background. Add proper motion to radial velocity and you get a three-dimensional speed through space. Space missions that measure positions with great accuracy make these maps precise, while spectra supply the missing line of sight component. Spectra reveal other motions too. When a star spins, one edge rotates toward us, while the opposite edge rotates away. Light from the approaching side is slightly blue shifted. Light from the receding side is slightly red shifted. The combined effect spreads each spectral line into a wider, smoother profile. The faster the spin, the broader the lines. The broadening also depends on the tilt of the rotation axis relative to us. What we measure is often written as v sin I, the rotation speed times the sine of the inclination angle. Two stars can have the same true spin but different v sin I if one is seen equator on and the other nearly pole on. Rotation is not the only driver of line width. Temperature broadens lines because faster thermal motion spreads the velocities of atoms. Pressure broadens lines through collisions in dense layers. Magnetic fields split lines into closely spaced components in a pattern called the Zeeman effect. In strong fields, this splitting becomes measurable and can map fields on stellar surfaces. Turbulence in a star's atmosphere adds its own small spreads. Careful fitting can separate these influences and tell us about temperature, pressure, fields, and motion all at once. Activity leaves marks as well. Dark spots, bright faculae, and flares change line depths and shapes over the rotation period. As a spotted star spins, those asymmetric features move across the visible disk and distort line profiles in a repeatable way. This can mimic or hide the small signals of planets, so exoplanet searches often track activity indicators, specific lines sensitive to magnetic heating, to disentangle surface changes from true orbital motion. Color still links back to temperature and structure. The spectral class O, B, A, F, G, K, M tells the broad temperature range. The decimal digit refines it. The luminosity class I, 2, 2, IV ties in size and surface gravity. A label like G2V compresses a lot of physics. Surface temperature near that of the Sun, lines shaped by a dwarf's gravity, and a stable main sequence core burning hydrogen. An M23 is cooler and larger, with low gravity broadening different sets of lines and a spectrum rich in molecules that can't survive in hotter photospheres. Hydrogen lines shift in strength with type. In A-type stars near 10,000 K, Balmer absorption is strongest because many hydrogen atoms sit in the right state to absorb visible light. In cooler K and M stars, hydrogen lines weaken, and molecules like titanium oxide produce broad features. In hotter O and B stars, hydrogen is more ionized, and helium lines dominate. These patterns help classify stars quickly, even in noisy data, and they carry over to galaxies, where the mix of stellar types shapes the overall spectrum. All of this depends on instruments that stay stable for hours and nights. High-precision spectrographs are temperature-controlled and pressure-controlled. They use reference light sources such as emission lamps, iodine cells, or laser frequency combs to set a firm wavelength scale. They track tiny drifts and correct them before they mimic real signals. In the infrared, detectors must be cooled to reduce their own glow. In the ultraviolet, space platforms carry the load because air blocks the light. Each band comes with its own engineering challenges, but the goal stays the same: measure wavelengths and intensities with enough fidelity to trust the physics we extract. Spectroscopy has also moved beyond the largest observatories. Compact gratings, fiber feeds, and sensitive cameras let small telescopes collect decent spectra of bright stars, variable stars, and comets. Students and amateurs can record hydrogen's H-alpha in emission nebulae, see sodium's doublet in street lamps and the moon's reflected light, or measure how a bright star's lines shift during an eclipse in a binary system. The same principles scale from a backyard to a flagship space mission. Across all these uses, the logic repeats. Light carries structure. Instruments spread that light out. Lines appear where atoms absorb or emit. Shifts and shapes encode motion and conditions. Models translate those patterns into temperatures, densities, speeds, sizes, and fields. The more carefully we measure, the more we can say. Stars, in short, are not fixed or silent. They move through space, tugged by gravity. They circle companions, some host planets, and wobble under their pull. They stream in clusters and drift apart over time. Spectra let us see those motions clearly and quantify them. They also show us internal motion at a surface we cannot touch, reading rotation from line profiles and measuring how fast a star spins. It can also tell us if it's spinning. When a star rotates, different parts of its surface are moving in different directions. Astronomers use metals to mean everything heavier than helium. It's a shortcut that separates the primordial mix from what stars later made. In practice, we measure metal content with spectra. The strength of iron lines compared to hydrogen gives a value called Fe-H. A negative number means fewer metals than the sun. A positive number means more. Ratios between elements add more detail. The balance of alpha elements like oxygen, magnesium, silicon, and calcium relative to iron traces how quickly a region formed stars because different kinds of supernovae make these elements on different timescales. A spectrum becomes a chemical ledger that records not only what a star is, but where and when it formed. That chemical story splits stars into broad families. The first generation, made almost entirely of hydrogen and helium, are called Population 3. They were massive and brief, and we have not yet seen one directly. The next generation, population 2 formed from gas enriched by the first supernovae. They are metal-poor and old, common in the halo of our galaxy and in globular clusters. Population I stars, like the Sun, are metal-rich and live mostly in the disk. Their spectra show stronger metal lines and more complex chemistry. This layout appears across many galaxies: older, metal-poor stars in halos, younger, metal-rich stars in disks and spiral arms. The pattern is not random. Metals build up over time because stars make them, and dying stars return them to space. Massive stars end in core collapse supernovae and enrich their surroundings quickly with oxygen, magnesium, and similar elements. Some white dwarfs in binary systems reach a critical mass and explode as type Ia supernovae. They make a lot of iron group elements on a slower clock. Mix the two, and you get the observed element ratios. In a spectrum, you can see the fingerprints of both processes, oxygen and magnesium lines telling one part of the story, iron lines telling another. Heavier than iron elements need different routes. One path is the slow neutron capture process inside aging giant stars. Over long periods, these stars add neutrons to existing nuclei, step by step, and later release the products in stellar winds. Another is the rapid neutron capture process during violent events with many free neutrons. Observations of some kilonovae explosions that follow neutron star mergers show elements like strontium in their spectra. In old, metal-poor stars, strong lines of barium or europium reveal which process dominated their birth cloud. Even on the far edge of visibility, light tells us how the periodic table spread. Because spectra carry chemistry, they also carry time. Stars born when the galaxy was young tend to be metal-poor. Stars born later, after many cycles of birth and death, are metal-rich. By reading Fe, H, and element ratios, astronomers estimate ages and map how the Milky Way assembled. They find gradients. The inner disk is, on average, more metal-rich than the outer disk. The halo is metal-poor and clumpy, with streams that mark long-ago mergers. This galactic archaeology is done with light alone, one spectrum at a time. Metal content matters for planets. Dust, the solid part of protoplanetary disks, is made from metals in the astronomical sense. Silicates, carbon grains, ices with oxygen and nitrogen. More metals mean more raw material to build planet cores. Surveys show that stars with higher Fe, H, are more likely to host giant planets. That link is read from starlight as well. The star's spectrum tells its metal content, and small, periodic line shifts reveal the tug of planets. In certain cases, spectra during a transit even show sodium or water vapor in the planet's atmosphere. The same trick that names elements in a candle flame names gases on a world light years away. Spectra also age-date star clusters. In a cluster, all stars formed around the same time. On a color temperature plot, the turn-off point, where stars leave the main sequence, marks the cluster's age. Spectra refine that picture by giving precise temperatures, gravities, and metal content for many members. A single deep exposure that spreads a cluster's light can even act like a composite spectrum, from which models recover the mix of stellar types and the cluster's history. The light from gas clouds has its own codes. Hot, thin gas near young stars glows with bright emission lines from hydrogen, H-alpha, H-beta, oxygen, O3, OT, nitrogen, and sulfur, S2. The relative strengths of these lines diagnose temperature, density, and the hardness of the radiation field. Useful line ratios separate regions lit by newborn stars from those excited by shocks or by energy from a growing black hole. Cooler molecular clouds do not shine in visible light, but glow in the radio and millimeter bands. Carbon monoxide lines trace dense, cold gas, the raw material for future stars. Even in the visible, faint, diffuse interstellar bands ride on stellar spectra, probably from complex molecules. Dust reddens the light and leaves a slope that can be measured and corrected, restoring intrinsic colors and luminosities. On larger scales, spectra reveal galaxy evolution. A galaxy rich in recent star formation shows strong hydrogen emission and a blue continuum from hot, young stars. A quiescent galaxy shows deep absorption features from older, cooler stars and little or no emission. Redshift moves the entire pattern toward longer wavelengths, letting us line up nearby and distant spectra on the same scale. With enough spectra across cosmic time, we watch the average star formation rate rise to a peak billions of years ago and then decline. We also track how metal content grows with galaxy mass. Heavier galaxies tend to keep their metals, while lighter ones lose some through winds and outflows. All of these trends come from light passed into lines. Motion remains a major part of the picture. A rotating star broadens its lines. A turbulent atmosphere adds small extra width. A magnetic field splits certain lines into multiple components. By fitting line shapes, we recover rotation speeds, turbulence, and field strengths. In rapidly rotating stars, the equator can bulge and cool slightly relative to the poles. This gravity darkening leaves subtle imprints on spectra and on the light curve when such a star is eclipsed. In close binaries, gas flows and winds can sculpt line profiles into asymmetric forms that vary over an orbit, letting us map the interaction between the stars. Pulsations open another door. Some stars expand and contract in regular cycles. Their surfaces speed up and slow down in step with brightness changes. The Doppler shifts across a cycle, together with the light curve, tell us about the layers moving inside. This is asteroseismology in its simplest form. With dense data, the small frequency spacings between different pulsation modes reveal internal structure. Much like seismic waves reveal Earth's interior, space missions that measure light with extreme precision supply the timing. Spectra supply the velocities and temperatures that complete the model. The Sun provides a nearby laboratory. High-resolution solar spectra measure flows across the surface, follow oscillations, and track the change of line shapes in active regions. Differences in line strength near sunspots and plages show how magnetic fields heat the chromosphere. Small, steady blue, or red shifts across granules record rising hot gas and sinking cool gas. The same physics applies to other stars, but the Sun lets us resolve it directly and then scale the results outward with confidence. Detecting planets often requires removing stellar activity signals from the radial velocity data. Spots and faculae that rotate in and out of view distort spectral lines and can mimic a planet's tug. Activity indicators like the calcium H and K lines flag when the star's surface is changing. By modeling those changes, observers isolate the true periodic shifts from orbiting planets. Combining radial velocity with transits is especially powerful. The transit depth gives size, the velocity amplitude gives mass, and together they give density. A dense small world is likely rocky. A low-density larger one is puffier, with a thick atmosphere. Transmission spectroscopy extends that reach. During transit, a thin ring of the planet's atmosphere filters starlight. Certain wavelengths are absorbed slightly more, producing tiny extra dips at those wavelengths. Sodium and potassium have been seen this way, along with water vapor and sometimes carbon-bearing molecules. For very hot, close-in planets, emission and reflection spectra during other phases add more constraints, revealing temperature structures and day-night differences. The signals are weak, but persistent observation builds them up. Gravitational microlensing adds surprises. When a foreground star passes almost directly in front of a background star, gravity magnifies the background light for days or weeks. If the foreground star has a planet, it can create a brief extra bump in the brightness curve. Spectra taken during such events can confirm the nature of the foreground star, and sometimes the background one. The method is sensitive to planets far from their stars, and even to low-mass bodies. Direct imaging works in special cases. Young, massive planets far from their stars glow in the infrared and can be seen next to their dimmed host with careful optics. Once imaged, their spectra reveal clouds, molecules, and temperatures. In all of these methods, timing ties to wavelength. A repeating light dip confirms a transit. A repeating velocity shift confirms a wobble. A line that appears only during transit likely belongs to the planet's atmosphere. A line that broadens and shifts across a rotating stellar disk maps the star's spin. None of this requires touching the source. It requires stable instruments, careful calibration, and enough photons to beat down noise. Even the faintest light can be useful if collected long enough. Large telescopes and long exposures make spectra of distant galaxies. Stacking many similar spectra raises weak features above noise. Space observatories that work at very cold temperatures reduce the glow of their own instruments, allowing infrared spectra of the earliest galaxies. In that regime, Lyman alpha and other key lines have slid out of the visible into bands where only space can see them cleanly. The position and shape of those lines place the object in time and hint at the gas around it, which can scatter or absorb the light. Starlight also marks outflows and inflows in galaxies. Blue shifted absorption can show gas blowing toward us from a starburst. Red shifted absorption can show gas falling in. Emission line widths and ratios trace shocks and winds. Over many objects, a pattern appears. Small galaxies more easily drive outflows that remove metals. Massive ones hold on to their gas and enrich it. These flows affect how quickly stars form and how quickly planets can arise. Back closer to home, spectra monitor variable stars that serve as distance markers. Cepheids have a tight relation between their pulsation period and their true brightness. Measure the period and apparent brightness, and you have distance. Spectra during the cycle refine the temperature and motion, improving accuracy. Another step outward uses Type Ia supernovae. Their spectra show a strong silicon line and a standard shape near peak brightness. After correcting for stretch and color, they act as bright beacons across cosmological distances. Redshift in their spectra then couples with distance to map the expansion rate. Everywhere we look, the same pattern holds. The universe writes in light. Hydrogen and helium provide clean anchors. Heavier elements add detail. Motion shifts lines and broadens them. Temperature sets which lines are strong. Density and pressure adjust the widths. Magnetic fields split some lines. Dust reddens the continuum and imprints faint bands. The instruments that read all of this, gratings, prisms, cooled detectors, stable optics, turn the sky's glow into numbers. The numbers turn into temperatures, speeds, abundances, and ages. A rotating star leaves broader lines than a slow one. A fast rotator can bulge at the equator, making the poles hotter and brighter than the midsection. That uneven surface brightness affects the light we see and the shape of spectral lines during eclipses. Binary stars reveal themselves as pairs of shifting patterns, where only one pattern is seen. Timing still gives masses and orbits. Pulsating stars make rhythmic line shifts. Winds carve asymmetries. Flares alter certain activity-sensitive lines for minutes to hours. The sun shows all of these in miniature and teaches us how to read them elsewhere. From the faintest galaxies to the nearest star, from the earliest atoms to the latest planets, the path is consistent. Photons carry structure from their source, pass through space, and arrive with that structure intact, except for known changes from dust, gravity, and expansion. Spectroscopy is the method that unfolds that structure. It shows us that a point of light is not simple. It is layered with motion, chemistry, and history, and those layers can be read in the positions, shapes, and strengths of thin lines. Spectral lines change as the blast evolves. Early on, the ejecta are dense and hot. We see broad features, not narrow ones, because the gas is racing outward at thousands of kilometers per second. That speed stretches and blends the lines into wide troughs and humps. In core collapse events type 2, hydrogen leaves a clear signature with a shape called a P Cygni profile, a bright emission bump with a notch of absorption shifted to the blue. The notch forms because fast-moving gas in front of the explosion absorbs light on its way to us. The position of that notch reveals the expansion speed. Day by day, the notch slides as the gas thins and slows, letting us clock the blast in real time. Type Ia supernovae thermonuclear white dwarf explosions tell a different story. In the days around maximum light, a deep absorption near 615 nanometers shows singly ionized silicon, Si. That line is a flag that we are seeing burned material from carbon and oxygen turned into intermediate mass elements. As the ejecta expand and cool, lines from ion group elements grow stronger. These lines come from the ashes of the runaway fusion that tore the white dwarf apart. The early lack of hydrogen, paired with those silicon and iron signs, is a clean way to sort type Ia from type 2 with a single spectrum. Brightness alone is not idle glow. It is powered by radioactive decay. In both families, but especially in type Ia, a large mass of nickel 5,6 is made in the fireball. Nickel 5,6 decays to cobalt 5,6 and then to stable iron 5,6, releasing gamma rays and positrons. That energy diffuses out and lights the fading supernova over weeks and months. The shape of the light curve, the fast rise and slower fall, tracks how photons random walk through the expanding debris and how the decay power declines with time. Spectra taken along the light curve show a handoff. Early features from hot, opaque layers give way to late nebula spectra, with many forbidden lines from iron, cobalt, and calcium. In that stage, the ejecta are thin enough that we look straight into the products of the explosion, and the line width still encodes speeds of several thousand kilometers per second. Type 2 events split further by behavior. If the star kept a thick hydrogen envelope, the light curve often shows a long, flat plateau as hydrogen recombines and releases stored energy. These are type 2 IP. If much of the envelope was lost before the blast, the light declines more quickly, type 2IL, when the expanding shock runs into dense gas shed by the star in its final years. The shock lights that gas, and we see very bright, narrow emission features riding on the spectrum, type IN, the N for narrow. Those narrow lines trace the slow wind that left the star, and the broad wings trace the fast ejector slamming into it. The details of these lines reveal mass loss histories in the last months and years of a star's life. Stripped envelope supernovae, types IB and IC, show what happens when massive stars lose most or all of their outer layers before they die. Type IB lack hydrogen, but show helium. Type IC lack both hydrogen and helium at observable levels. Their spectra near peak show blends from oxygen, calcium, and other intermediate mass elements, with very broad features indicating high speeds. Some IC events are broad-lined, tied in a few cases to long gamma-ray bursts. In those spectra, the usual features are so smeared that identifying them requires models, but the extreme widths say plainly, this blast was fast. A powerful trick for reading supernova geometry is polarization. If the ejector were a perfect sphere, scattered light from different parts cancels out, and net polarization is small. Asymmetries caused by jets, clumps, or lopsided explosions leave residual polarization in the continuum or even across single lines. Spectropolarimetry maps those changes with wavelength, revealing shapes we cannot resolve directly. Many core collapse supernovae show polarization that evolves with time, suggesting clumpy or elongated debris. Type Ia often show low continuum polarization, but sometimes line polarization, hinting at structure in the outer layers of burned and unburned material. Not all the action is in the star itself. The moment the shock reaches the surface, a brief shock breakout can flash in ultraviolet or X-rays, sometimes caught by fast survey telescopes. Afterward, the shock heats surrounding dust and gas, which can re-radiate in infrared. If the blast plows into a dense circumstellar shell, the spectrum fills with interaction signatures that can persist for months or years. Radio and X-ray emission rise as particles are accelerated in the shock, and magnetic fields amplify. Those signals complement the optical spectrum by tracing the fastest and thinnest regions. Time is a tool here. A series of spectra taken night after night is like a flipbook. Features shift, narrow and fade. New ones appear as deeper layers become visible. Early spectra diagnose the outer skin, what the star lost or kept before it died. Middle spectra trace the bulk yields: oxygen, magnesium, silicon, calcium. Late spectra in the nebula phase expose the core products, iron group lines spread across thousands of kilometers per second. Modelers compare these sequences to explosion simulations to estimate ejector mass, nickel mass, mixing, and asymmetry. The fits are not guesswork. They must match line positions, widths, and strengths across many wavelengths at many times. Sometimes, a nearby event teaches the most. In 1987, a blue supergiant exploded in the Large Magellanic Cloud. Its spectra evolved in full view for years. Rings of gas around the star, thrown off long before the blast, lit up as the shock reached them. The sequence tied spectra to known distances and let astronomers weigh the nickel by following the late-time light. That playbook is now applied to other events farther away, with new instruments reaching deeper and faster. Superluminous supernovae stretch the scale. Their spectra can look like extreme versions of Type 1 or Type 2. but their light curves are 10 to 100 times brighter than common events. Power sources may include interaction with dense shells, energy from a rapidly spinning magnetar formed in the core, or, in rare cases, exotic nuclear burning. The broad features, unusual line ratios, and very slow evolution push models, hard, infrared spectra, ultraviolet coverage, and polarization are often needed together to narrow the options. All of this matters beyond the explosion. The elements made and ejected set the stage for future stars and planets. Oxygen and carbon from core collapse events enrich star-forming clouds. Iron group elements from type Ia raise the average metallicity over billions of years. Spectra of supernova remnants, long after the light curve has faded, still carry the imprint. Bright lines from shocked oxygen in some remnants, iron-rich knots in others. X-ray spectra in particular show line complexes that map temperatures and compositions in hot plasma, linking back to the kind of explosion that occurred. Type Ia supernovae carry a special role as distance markers. Although not identical, they can be standardized. Brighter events fade more slowly, and their colors correlate with intrinsic brightness after correcting for dust. With those corrections, type Ia act as standardizable candles across vast distances. Their spectra near peak confirm the type silicon present, hydrogen absent, and refine the corrections by diagnosing dust and metallicity. Distances from these events, combined with redshifts, map the expansion history of the universe. When many were measured at large look-back times, the data implied that expansion is accelerating. Today, large surveys keep improving the sample. Spectra remain central to the method, both to classify objects cleanly and to track how populations may evolve with time. Not every spectrum is clean. Dust can redden and dim the light, changing line depths and colors. Host galaxy light can blend with the supernova signal, especially for events near bright galactic centers. Narrow absorption from gas in the host or in our own galaxy can cut small notches into the continuum. Careful subtraction and calibration are needed to isolate the ejecta features, and multiple telescopes often share the work, some catching early ultraviolet, others following the near-infrared, still others returning months later for the faint nebular phase. The tools built for this work are specialized. Low-resolution spectrographs classify new events quickly. High-resolution instruments pick apart narrow interstellar lines and measure tiny velocity shifts. Integral field spectrographs take a spectrum at every point in a small field, building a 3D cube, 2 spatial axes, 1 wavelength axis, that separates the supernova from its host and maps emission across a region. Space telescopes supply ultraviolet spectra above the atmosphere. Large, cold instruments supply infrared spectra free of thermal glow. All chase the same goal: capture enough photons with enough fidelity to let the physics speak. Beyond classification, line profiles give geometry. A symmetric, boxy profile can indicate a shell. A skewed profile can point to dust forming inside the ejecta, absorbing redshifted light from the far side and making the blue wing look stronger. Multiple components can show separate velocity systems, perhaps a jet or a dense clump. Monitoring these shapes as they evolve distinguishes between dust formation, changing ionization, and true bulk flows. Pulses and plateaus in the light curve tie to spectra in useful ways. During a plateau in a Type 2 IP, hydrogen lines stay strong, while the temperature inferred from the continuum cools and then stabilizes as recombination sets in. Near the end of the plateau, lines shift and the spectrum transitions to the nebula phase. In type Ia, the timing of the silicon line strength relative to peak light feeds into the standardization for distances. Late-time iron lines fade according to the cobalt decay rate, letting us measure how much radioactive nickel was made. As the debris thins, some explosions reveal narrow lines from elements excited by the decaying radiation field. These lines act like test lamps inside the ejector, turning on when conditions are right. Their presence or absence helps separate models that differ mainly in mixing. If the inner iron group elements are mixed into the outer layers early, iron lines appear sooner. If not, they rise later, and the early spectrum stays dominated by intermediate mass elements. The timing is a clock that counts how the layers were stirred. The environment around the star leaves clues, too. If the progenitor shed a lot of mass shortly before the blast, we might see flash ionization features, very narrow lines that appear in the first day or two and then fade as the nearby gas recombines. Catching these requires rapid response spectra within hours of discovery. When seen, they pin down the chemical makeup and density of the immediate surroundings, giving direct evidence for the final acts of the dying star. Helioseismology inspired a related approach in exploding stars by tracking tiny changes in line positions across the photosphere as the ejecta expand, and by comparing those with simple models. We can estimate distances with less dependence on external calibrations. For some subclasses of Type 2, this expanding photosphere method turns spectra and broadband colors into absolute sizes and, therefore, distances. It is a cross-check on other ladders and works well for events close enough to resolve early. When supernovae interact strongly with their environment, the spectra can persist for years. The broad components narrow, forbidden lines strengthen, and the relative intensities shift as temperatures and densities change. In a few cases, light echoes scattered by distant dust sheets deliver delayed copies of the early spectrum to us years later. Those echoes let us re-observe the blast at multiple times from different lines of sight, a rare chance to test symmetry from nature's own archive. Across all of these threads, the pattern is consistent. Light encodes motion, makeup, and shape. Instruments decode it. Models translate it into physical pictures. An early spectrum sorts the class. A sequence maps the layers. The late phase exposes the core products, the lines themselves broad or narrow, symmetric or skewed, strong or faint, carry the clues. And when the blast is tied to a binary white dwarf, or to a massive star at the end of its life, those clues point to the path that led there, and to what the explosion returned to space for the next generation of stars and planets. Because they were so short-lived and lived so early, catching them in the act is hard. Their light has been stretched by the expansion of space into the infrared, and most of them were gone long before today's galaxies settled down. Even so, we can look for their fingerprints in two ways: by finding their chemical wake in later stars, and by searching for the special kinds of light their first galaxies might still send us across time. The chemical wake shows up in ancient, metal-poor stars in our own galaxy. These stars formed from gas that had been touched only lightly by the first explosions. When we split their light, we see almost no heavy elements at all, sometimes a few parts in 100,000 compared with the Sunday. Certain patterns are telling. If a star shows a lot of carbon relative to iron, or very odd ratios among elements like magnesium, calcium, and titanium, it may have been seeded by a very early supernova with unusual yields. These fossil stars do not show us population 3 directly, but they preserve the ashes those first stars made. Reading them is a kind of archaeology done with spectra instead of shovels. The direct search aims at the deep sky. Very distant galaxies, seen when the universe was only a few 100 million years old, sometimes glow in specific lines of hydrogen and helium. One clue is the helium line called He2 at a wavelength of 1,640 angstroms in the ultraviolet. Hard, hot radiation from extremely massive, metal-free stars can light this line strongly. If we see a compact galaxy with bright He2 and little sign of metals, that raises the possibility of a population 3 burst. Another clue is strong Lyman alpha emission from hydrogen. In very young galaxies, this line can be intense, though it is easily scattered by the fog of neutral hydrogen that filled the early universe. If Lyman alpha still leaks out, it hints at hot stars carving bubbles in that fog. There is a broader backdrop to this hunt: the cosmic dawn. After the Big Bang, the universe cooled and went dark. Gravity slowly gathered gas into small halos of dark matter, tiny by galaxy standards, with masses 100,000 to a few million suns. In those mini halos, hydrogen molecules formed and helped the gas lose heat. As the gas cooled, it condensed without much fragmentation. Because metals and dust, the efficient coolants, did not yet exist, the result was fewer, larger stars. The first ones turned on, flooded their surroundings with ultraviolet light, and began to ionize hydrogen. Many likely died in spectacular supernovae within a few million years, sending shock waves through the small halos and stirring the gas for the next round of starbirth. That light from the first stars did something else important. It started the long process of reionization. The intergalactic medium, once neutral, became ionized again as ultraviolet photons knocked electrons off hydrogen atoms. This transition was not instant. It happened patch by patch as bubbles of ionized gas grew and overlapped. Looking for the edges of those bubbles is one way to find where early stars lived. One proposed marker is the faint radio signal from neutral hydrogen at a wavelength of 21 centimeters. As the first light sources heated and ionized their neighborhoods, the 21 centimeter signal changed in strength. Mapping that change is like watching the fog lift at dawn, except the fog is hydrogen, and the light is ultraviolet starlight and X-rays. Supernovae from the first generation may also leave unique signatures. Some very massive, metal-free stars might explode as pair instability supernovae. In such a star, intense radiation creates pairs of electrons and positrons, softening the pressure that holds the core up. The star collapses and then blows itself apart completely. No compact remnant, just an enormous outpouring of heavy elements with a pattern distinct from later, more common explosions. If we find a star today with an element pattern that matches those, yields very high amounts of certain intermediate mass elements and very little iron, it could point back to this rare kind of early blast. In the deep sky, a pair instability event would be extremely bright and slow to fade, and its spectrum would evolve in a characteristic way, with broad oxygen and magnesium features dominating for a long time. Catching one at great distance would be difficult, but not impossible with sensitive infrared instruments. Gamma-ray bursts offer another window. Some long GRBs come from the collapse of very massive stars. Their afterglows are bright beacons that can be seen across much of the visible universe. If one went off in a very young, metal-poor galaxy, Its afterglow spectrum could show us both the near-zero metal gas around the burst and the intergalactic medium in front of it. The timing is tricky because the afterglow fades quickly, but the reward is a clean sightline through the early universe with a backlight powerful enough to print thin absorption lines from otherwise invisible gas. Closer to home in time but still far in distance, we can watch the first small galaxies grow into larger ones. Early systems are often clumpy and irregular. Their spectra show strong hydrogen and helium features and, at first, very weak metal lines. As star formation continues and supernovae enrich the gas, oxygen, carbon, and nitrogen lines strengthen. By comparing many galaxies at different redshifts, astronomers build a timeline of enrichment: how fast metals built up, how quickly dust formed, and when the balance tipped from population 3 style conditions to the normal star formation we see later. The trend is uneven. Some regions enriched quickly, others remained pristine pockets for a while, allowing late population 3 pockets to light up even after the first wave had passed. The first black holes enter the story here too. Some were the direct remnants of the earliest massive stars, with masses of tens to a few hundred suns. Others may have formed by more exotic routes, such as the direct collapse of dense gas clouds that failed to fragment into stars. However they began, some early black holes grew fast, fed by streams of gas in young galaxies. Their accretion disks glowed, and their light ionized and heated the gas around them. Spectra of those young active nuclei show very broad lines from fast-moving gas near the black hole and narrow lines from more distant gas. The presence of strong, high ionization lines with very small metal content would be a hint that we are seeing a black hole lit by a near-pristine environment. As metals rise, the line ratios shift. Reading those ratios tells us about both the engine at the center and the chemistry of the host. So what, exactly, are we looking for when we claim a population 3 signature? Several pieces that fit together. A very high redshift, so we know we are seeing early times. Strong helium lines without corresponding metal lines. Very hot, blue continua that point to intense ultraviolet fields. And weak or absent dust features, because dust needs metals to form. If, in addition, we see neighbors with patchy Lyman alpha emission and signs that the surrounding hydrogen is still partly neutral, the case grows stronger. The standard of proof is high. Other sources, like very low metal starbursts or active black holes, can mimic some of these features. That is why the most convincing cases use multiple lines, multiple instruments, and time series to track how the light changes. The physics behind the first star formation can be sketched in simple terms. Gas falls into a dark matter halo. As it piles up, it heats. To keep collapsing, it must shed that heat. In today's clouds, metals and dust radiate that heat away efficiently, and the cloud breaks into many small fragments. In the early universe, without those coolants, the main path to losing heat is through molecular hydrogen H2 lines. H2 is harder to form and less efficient at cooling. The cloud cannot fragment as much, so the pieces that do form are more massive. The forming star gains matter from a disk and may launch outflows that limit its final mass, but in many models, the result is still a star far larger than those common today. Its lifetime is short, its light is harsh, its end is swift. While the first stars were rare and brief, their impact was outsized. They seeded the universe with the first carbon, oxygen, silicon, and iron, Their ultraviolet light carved channels in the fog of neutral hydrogen. Their shocks stirred and mixed gas in and between the first halos. Their remnants, if any, may have been the seeds of the black holes we see later at the centers of galaxies. Each of these effects leaves a spectral trail: enhanced oxygen in the next generation of stars, patchy Lyman alpha transmission through reionization, early dust forming in supernova ejecta and showing up as infrared glow, and, in a few cases, unusual element patterns that point to exotic explosions. Back on the fossil side of the hunt, extremely metal-poor stars in the Milky Way's halo carry detailed stories. Some show high carbon with almost no iron. Others show enhancements in elements made by rapid neutron capture, hinting that a nearby neutron star merger may have happened early in their history, though whether such events were common that early is still debated. By measuring dozens of elements in a single ancient star, astronomers pieced together which kinds of explosions enriched its birth cloud. The match is never perfect, but patterns emerge. Some stars bear the hallmarks of a pair instability event: strong intermediate mass elements and very low iron. Others look like the products of more ordinary core collapse supernovae. The variety tells us that the first generation may already have included multiple mass ranges and explosion types. Even the emptiness between galaxies talks. Bright background sources, quasars, and some galaxies shine through diffuse gas that imprints thin absorption features across a wide span of wavelengths. At high redshift, a thick, dark trough appears blueward of Lyman alpha, where neutral hydrogen blocks most light, the Gunn-Peterson trough. As reionization proceeds, that trough fills with narrow spikes where light slips through bubbles and gaps. Metal lines, when they appear at early times, are clues to where and how far the first supernovae spread their products. Often we see carbon and oxygen first, then silicon, then a richer mix. The timing and strength of these lines map the spread of metals through space. Galaxies themselves offer a composite record. Their starlight shows the mix of ages and temperatures in their populations. Their emission lines show current star formation and gas conditions. Their absorption features show older stars and interstellar gas along the line of sight. In very young systems, the continuum is blue and the metal lines are weak. In older, quiescent systems, the continuum is redder and metal lines are strong and numerous. By comparing observed spectra to models built from many stellar types, so-called population synthesis, astronomers estimate star formation histories and metal growth over time. The models must include the changing initial mass function, the distribution of star masses at birth, which may have been top-heavy, favoring massive stars in the very early universe. If the earliest systems made more massive stars than later ones, their spectra would be harder, more ultraviolet, and their chemical yields would show distinctive ratios. Dust, born from heavy elements, is a latecomer, but an important one. It absorbs ultraviolet and visible light and re-emits in the infrared. Its presence reddens spectra and hides some lines while boosting infrared output. If we see a very young galaxy with strong ultraviolet light and little infrared re-emission, it likely has little dust, yet consistent with a near pristine state. As dust builds, the spectrum changes character. Lines formed in the gas may be partially hidden, and the shape of the continuum bends. Measuring those bends and the silicate or carbon features that ride on them tells us how quickly dust grew, which in turn depends on how many supernovae and evolved stars were already at work making heavy elements. In all of these threads, light is the common carrier. It travels a long way, but it keeps the details of where it came from. The trick is learning to separate those details, which lines belong to stars, which to gas, which to dust, which shifts come from motion and which from cosmic expansion, which ratios come from temperature and which from composition. The instruments that do this, gratings that spread wavelengths, detectors that count single photons, spectrographs tuned to the infrared, are built to be steady and precise. Their job is to keep faith with the photons so we can keep faith with the physics. As surveys go deeper, the map of early times gains features. Patches of ionized gas appear like islands in a dark sea. Clusters of small galaxies show synchronized bursts, perhaps triggered by shared flows of gas. Occasional bright transients puncture the dark, and their afterglows sketch the outlines of the medium around them. Among the oldest stars in our own halo, chemical oddities flag a few that formed from gas touched by only one or two early explosions. Put together, these pieces make a picture. The first stars were rare, hot, and heavy. They lit the first beacons. They made the first metals. They died quickly and spread their influence. And their echoes, though faint, can still be traced in the spectra of the youngest galaxies and the oldest local stars. The search is not a single observation, but a pattern. It is the helium line without metals in a tiny, distant source. It is the blue, hard spectrum of a near-pristine starburst. It is the absence of dust, where dust would usually glow. It is the iron pore, carbon-rich signature in a halo star. It is the patchy transmission of hydrogen's Lyman alpha through a still neutral universe. Each alone is suggestive. Together they are persuasive. And as instruments sharpen and patience accumulates, the simple hydrogen and helium beginning comes into clearer view not as a blank page, but as a first stanza written in hot, bright light, carried forward by photons that have crossed nearly all of time to reach us. We can't sweep the sky and find one of these first stars twinkling alone. Their light faded billions of years ago. Yet, like careful archaeologists, astronomers look for traces they left behind. The best clues come from light more precisely, from what's missing. A star's spectrum is shaped by the elements in its outer layers. Metal-rich stars show a crowded forest of absorption lines from calcium, sodium, magnesium, iron, and more. Metal-poor stars show fewer, shallower lines. A truly metal-free star, the kind we call population 3, would show an extraordinarily clean spectrum, marked only by hydrogen and helium. That theoretical signature has been modeled in detail, with temperature, pressure, and rotation all accounted for. If a telescope ever finds an unusually hot source with a smooth spectrum stripped of heavy element lines, it would be a strong candidate for a first-generation star or a small cluster of them. There is a catch. The light from such stars would be stretched by the expansion of the universe into the infrared. They lived more than 13 billion years ago, so their ultraviolet and visible light has slid far beyond the reach of ordinary instruments. That is why infrared observatories are crucial. With cold mirrors and sensitive detectors, they can catch the redshifted glow from the first stars and galaxies. Already, deep surveys have identified galaxies from times when the universe was less than 400 million years old, an era when patches of nearly pristine gas may still have been birthing metal-free stars. The targets we seek are galaxies with extremely low metallicity, systems where heavy element lines are weak or absent. Inside them, pockets of untouched gas could host brief bursts of population 3 star formation. We may never isolate a single ancient star, but we might detect the blended light of a small group shining faintly from the edge of time. There are indirect routes as well. Some supernova remnants in very distant galaxies may carry the odd elemental ratios expected from first-generation deaths, strong yields of carbon and oxygen, very little iron, and other patterns that do not match common modern explosions. Here at home, the most metal-poor stars in the Milky Way's halo could be the children of those first stars. They formed from gas that was barely enriched, then survived quietly for billions of years. With high-resolution spectroscopy, scientists read their element lists carbon, magnesium, calcium, iron, and dozens more, and work backward to infer what the original blast must have produced. The match is not perfect, but distinct patterns point to specific kinds of early supernovae and to the masses of the stars that made them. There is also the possibility that some first stars never exploded. If a star was extremely massive, 200 solar masses or more, it may have collapsed directly into a black hole. Those early black holes could have grown over time into the supermassive objects we now see in galactic centers. Some of the bright, distant quasars lighting the deep sky may be powered by the dark remnants of the very first generation. Their spectra, and the absorption imprinted on their light by gas along the way, become part of the same trail of clues. This search is science and detective work woven together. We cannot point a backyard telescope and catch a population 3 star in the act. We rely on patterns, on ratios, on missing pieces. It's like learning about the first people, not by their bones, but by the simplest tools their descendants kept using. Even silence speaks. The absence of metal lines in a spectrum can be as telling as a loud signal, and astronomy has a gentler advantage over most fields. Old light keeps traveling. It does not forget. The photons sent by the first stars are still on their way, threading between galaxies and clouds, arriving one by one at our mirrors and sensors. Somewhere in that reddened glow, the first lights of the cosmos are still present, at least in the waves that have not yet reached us. Each deep exposure pushes a little farther. Each spectrum adds a small note to a long chord. With time, these notes assemble into a theme, a universe that began plain, learned to build structure, and taught itself chemistry, star by star. The first stars lit the way, forged the first heavy elements, and handed the raw materials to later generations. Their direct faces may remain hidden, but their influence is everywhere, in the carbon in a leaf, in the oxygen we breathe, in the iron inside a compass needle. So when you look up and see what seem like simple points of light, remember what they carry. A star's color tells its heat. Its spectrum lists its ingredients. Tiny shifts in line positions reveal motion and spin, the pull of unseen planets, the pace of a galaxy's rotation. From those same shifts in faraway smudges of light, we learn that the universe expands. From faint, ancient afterglows, we read the last traces of the Big Bang. Light is not only illumination, it is communication. It speaks in wavelengths and intensities, in narrow lines and broad hums, in pauses where metals are missing, and in bursts where hydrogen shouts. Learn the grammar, and the sky becomes a library. That is the quiet power of starlight. It turns a night's view into a record of time. It makes a thermometer out of color, a chemistry set out of lines, a map out of small shifts. From the first luminous beacons to the spirals that grew after, light brings the news. Even the oldest light, dim and stretched to the limit, has something left to say. With steadier instruments and patient modeling, We are becoming fluent in this language. As you settle into the dark, hold that thought gently. The stars are not distant and mute. They are active and articulate. They have been speaking for billions of years, and tonight, their messages happen to arrive where you are. Let them pass across your senses like slow waves at low tide, steady, precise, unhurried. In that rhythm, the universe tells its story, one photon at a time. The night will carry it forward. The stars will keep shining.